Hello viewers, welcome to CAE for you. In this video, we will see how open source tools can be used to simulate complex physical problems of industrial use. To be more specific, we will see how transient thermal analysis can be performed with composite disc brakes. This video is not intended as a step-by-step tutorial to perform the thermal simulation. However, we will discuss the approach and the motivation for this methodology. So, carbon-carbon disc brakes have gained significant prominence because of their excellent thermal and structural properties. Though the application is more specific to aircrafts, the general principle can be derived for any similar applications. Owing to the complexity of the material properties, that is the orthotropic characteristic of composite material, it is important to calculate the temperature distribution so that the brake pads and the associated components can be designed within their safety limits. Further, the brake systems are fitted with safety devices against any bursting due to overheating of the components. Hence, a reliable prediction method is desired so that unsafe operations can be averted, and such systems are often referred to as brake thermal management systems. So, the numerical model that we are developing can be instrumental in designing and developing such a crucial safety systems for critical applications. Let us look into the typical construction of the brake assembly. We have a central axle on top of which there is a torque tube which is attached to the stationary part, and we have the brake discs, and on top of it the wheel hub over which the tire is mounted. The discs are actuated using a cylinder and it is rested with a thrust pad. Let us take a deeper look into the brake disc assembly. As we take a closer look, the rotor discs are attached to the wheel hub and the stator discs are attached to the torque tube. The discs are arranged in such a way that they can move in axial direction, however cannot be moved in radial direction. This is required for the braking action. Let us look in detail about the braking action. A braking force is applied at one end of the brake disc and there is a thrust pad on the other end which resists the axial motion. Now, since the disc can move in the axial direction, each disc are compressed and an interfacial pressure is developed which creates a rubbing action between the rotor and stator. This rubbing action generates the heat which essentially converts the kinetic energy into heat energy and it is dissipated to the surrounding, ensuring that the process is smoother. In order to ensure that this happens smoothly, it is desired to have a constant deceleration, which means the velocity should be decreased in a linear manner. The braking force is typically applied using an hydraulic piston where the hydraulic pressure is increased to an extent or in a manner which exerts the braking force, resulting in a linear reduction of the velocity till the stopping distance. The entire braking process can be now split into three sub-processes where heat is generated, distributed and dissipated. The axial force creates a radial and temporal pressure distribution across the interface, which creates the heat. It can be numerically calculated as the pressure distribution multiplied by the frictional coefficient between the surface to the relative velocity of the disk. Since in this case stator is stationary, it corresponds to the rotational velocity of the rotor. It is worth noting that the velocity varies linearly in the radial direction, and also because of the conversion of kinetic energy into heat energy, the velocity varies with respect to time also. Though we indicated this as three different processes, they happen all in a simultaneous manner, which means the temperature at any point of the disk is a function of the frictional effect and the thermal expansion and the amount of heat that is transferred to the surrounding through conduction, convection and radiation. Since already this is a complicated process, at this point of time we will keep radiation aside. So it is necessary to account for the flow field around the components so that the heat transfer between the disk and the surrounding can be effected, which obviously influences the temperature at any point. The challenges with the current approach is that it would be very well observed the entire process is coupled, which calls for a thermomechanical simulation along with simulating the flow field around the components. Simulating such a complex phenomena is not only resource consuming but also time consuming, and eventually leading to serious problems in terms of completing the required activity in time, because designers typically ask reasonably accurate solutions quickly so that they can avoid very costly mistakes in their design. Further, the coupled thermomechanical simulation practically prohibits analyzing multiple solutions because of the resource intense approach, which eventually ends up with lesser number of options being evaluated, which can end up either in increasing the number of testing and hence the cost, or missing such critical phenomena may end up into fatal accidents. So there is a need to develop a reasonably acceptable model with low computational overheads. Let us see if there could be some simplifications that can be achieved. Obviously, the coupled problem has to be converted into an uncoupled problem so that the simulation time can be accelerated and the need for computational resource can be reduced. Now, looking into the processes, the heat generated was has to be calculated based on the radial pressure, interface pressure. However, this should also equal to the rate change of kinetic energy. So we can replace the pressure calculation and fit with the rate change of velocity, which can be again converted into rate change of kinetic energy, which is nothing but the heat flux. Since the thermal expansion coefficient for composites are very less, we can safely assume that the contribution of thermal expansion in terms of modifying the pressure distribution can be small and can be ignored. Further, the flow field simulation can be substituted using fluid networks, which acts as a bulk heat sink in terms of transferring the temperature between the adjacent components. Further, at this moment, we consider that the major contribution comes from conduction and convection. So the radiation effects can also be neglected. Based on the aforementioned considerations, the coupled simulation has been converted into an uncoupled simulation. Further, since there is no need for pressure values, this is further simplified as only thermal simulation. We can expect that significant overhead reduction can be achieved by converting this coupled simulation into uncoupled simulation. So in order to calculate the velocity change, a linear variation is assumed considering the velocity to drop completely at the stopping time. Further, the instantaneous velocity calculated through this simple equation is used to calculate the change in kinetic energy. Normalizing with the area participated in the frictional contact, the heat flux can be evaluated and the same can be used for the thermal calculation. In order to make the calculations easier, a octave script has been generated in which the necessary values are fed in to get the flux values. It will be later shown that only the maximum flux or the initial flux is sufficient to do the calculations because of the facilities available in the software. Once the flux values are available, a cyclic symmetric model was created using Freecad along with torque tube and wheel hub. The same geometry has been meshed using Salome mecha. Necessary care has been taken to ensure that all the node sets are created consistent to the software requirement so that there are no conflicts in terms of cascading or decascading the MPCs. Since we converted this problem as a pure thermal analysis, only thermal material properties are required. Since this is a transient simulation, we will need density, conductivity and specific heat for all the materials. The typical material used for torque tube is steel. The typical material used for wheel assembly is aluminum and the surrounding fluid is considered as air. Here the orthotropic material property has been assigned for the composite discs so that the material properties vary only in the orthogonal direction. It is worth noting that the values have to be specified consistent to the units in which it is modeled, that is the geometry and the mesh, so that we don't get into unnecessary unrealistic results. Let us look into the animation of the results. it is useful to plot the results at various disks, particularly the stator disk and the interface temperature. We expect that the outer disk should experience a earlier decrease in temperature because they are surrounded by ambient air in comparison to the central disk, which are surrounded by the outer disk. It can be clearly seen from the graph that the time for cool down starts earlier to the outer disk than the inner disk. Further, the interface temperature is also below the allowable limit of 2000 degrees centigrade. Of course, the unit in which the graphs are plotted are in Kelvin. This indicates that we may not expect any damage to the brake system, and at the same time the physical process is more or less reflected in a consistent manner. However, it is recommended that a calibration study has to be performed in order to fine tune the variables and make the results as close as possible. We also notice that the temperature in torque tube or the stator can be correlated with the temperature at wheel hub, so that preemptive decisions can be made in order to correlate the temperatures and see if dangerous temperature levels could be obtained at the wheel hub. Of course, this would require multiple simulations and correlations to arrive at a more reliable transfer function between the measured temperature and the inferred temperature. Now let us look into the positive sides of this approach. Of course, this is easy to build. The simulation has taken less than couple of minutes in a 4-core machine with 16 GB RAM. The numerical model can be very well calibrated with the test results to improve the accuracy. This can be considered as an ideal model for optimization and sizing calculations during conceptual stage due to the extreme time efficiency and resource efficiency. Of course, this significantly reduces the need for running the coupled transient thermomechanical simulation, which can be reserved for the final verification of the detailed design. And if the correlations are sufficiently done, the coupled transient thermomechanical simulations can be completely avoided, by which we state that this can be considered as a reduced order physics based model. As a downside, we still see that a structural analysis has to be performed in order to assess the pressure distribution and hence the validity of constant heat flux across the interfaces. However, the point of action of pressure can be modified if permitted by the design to ensure a more uniform pressure distribution across the surface, which is also desirable in terms of getting the desired performance. If the distribution is strongly varying, then the regions can be partitioned and the pressure can be approximated as a piecewise function so that the solution can be more reliable. The film coefficient mapping of fluid elements could be tricky and it needs to be updated for each modification, which means this is a challenge from the software being used, that is Calculix. The user needs to be a bit careful in terms of modifying this film coefficient files so that it is mapped properly. However, this can be very well improved based on any script which can be built to negate this issue. Finally, the fluid network elements will be or may need to be created manually, and hence it has to be checked continuously as the mesh gets refined. However, these are all substantially manageable problems in comparison to the benefit that we get. So we propose that this methodology can be utilized to best harness the numerical tools for the prediction of such a complex phenomena. Hope you like this video. Thank you.